So because electricity is a flow of energy, uh, we need to take into account ways that we can store that energy if we're getting our electrical energy from a flow. If we're getting it from a fuel like coal, we can say, okay, let me burn some more coal, I'll produce some more electricity. Then I turn down my coal furnace to produce less electricity. There's some lag time effects and things like that you have to worry about. But if you're producing your electricity from windmills, when the wind is blowing, electricity is coming out. When the wind stops blowing, boom, the electricity is gone. And since we are used to having our electricity always there, that's not so good. So for our renewable sources of power are by definition flows of energy. And for those, if we're using that to get our electricity, because those flows are not perfectly continuous and predictable. Hydropower is fairly continuous and predictable. The river flows at very predictable rates. You dam it up and you control the amount of water going through. But for solar and wind, which are becoming much, much greater parts of the electrical energy picture, um, the wind is not constant. The amount of sunlight reaching a solar power system is not constant. So in order to even out those fluctuations in the production of electricity from those inconstant renewable energy sources, we need to look at energy storage. So this chart shows on the horizontal axis the amount of energy stored in a kilogram of whatever the thing is. A kilogram of a battery, a kilogram of gasoline, a kilogram of coal. On the vertical axis, it shows the amount of energy stored per liter, which is a volume. It's about the size of a quart of that stuff. So uh, that tells you how much physical space you need for it. And on the horizontal axis, that tells you how heavy it is. So you can see that where you want to be is in the upper right-hand corner. That means you have a lot of energy in a small space and with not a lot of mass. And not surprisingly, that's where we find our fossil fuels. That's one of the reasons they're such awesome fuels, is that they've got a lot of energy stored very efficiently and very compactly. And you'll notice that batteries are way down, mostly in the lower left-hand corner. And these are a logarithmic plot. So the lithium ion battery dot there is at about 1 megajoule per kilogram and 1 megajoule per liter, whereas gasoline is at 100 megajoules per kilogram. So uh, you get literally 100 times more energy stored in a kilogram of gasoline than in a kilogram of a high-tech battery. So that's a challenge with finding good energy storage. But you'll notice in the upper right-hand corner, also at 100 megajoules per kilogram, is liquid H2 and H2 at 5,000 psi. That's gaseous hydrogen in a high pressure tank. And so those take up a little bit more space than a gallon of gasoline, but in terms of the amount of material you've got, uh, they are very good. That's a very good energy storage. Now, unlike coal and gasoline, I can't just go dig up liquid molecular hydrogen or gaseous molecular hydrogen, but what I can do is I can create it. I can use energy to create it, and therefore I have stored the energy by taking my electricity and using it to make a whole bunch of molecular hydrogen, which I can store in a tank, which I can then burn in a fuel cell to get my electricity back out. There'll be some inefficiencies there, as there are with any storage. So H2, it's very easy to create it electrically from water. Water is H2O. Put electricity into water, it splits into H2 and O. Separate them, then you just recombine them in a fuel cell and you get the electricity back out. So when people talk about hydrogen and fuel cells, hydrogen is a storage device for electricity that can be a very efficient means of storing that electricity and part of a picture of sort of electrification from renewable energy sources such as solar and wind. Check out your other online resources for studying solar technology. This picture is, I think, the author of the textbooks, Solar Power System, and he's got a Tesla battery that stores 6 kilowatt hours of energy. You say, oh, wow, that sounds like a lot. 6,000 watt hours, 6 kilowatt hours. Remember how much a kilowatt hour of electricity is worth? About 13 cents. So this battery stores about 80 cents worth of electricity, and it's huge. That shows you the challenge of batteries. And if you remember, I believe in an earlier homework assignment, you calculated what's the equivalent amount of energy in terms of gasoline stored in an electric car's battery. And that giant many 100-pound electric car battery is the equivalent to a couple of gallons of gasoline. Other storage technologies that are talked about, and in particular talked about in the book Sustaining Energy Without Hot Air, are at the power plant. You can, if the geography lends itself to that, you can use the electricity to run a pump and pump water uphill to a reservoir at the top of a hill. And then, say, if you're using solar energy at night, you can let that water run from the reservoir back down through that pump, and it turns the generator and it makes electricity again. The problem with that uh, technology, it works beautifully, but the problem with it is you've got to have the right geography. You've got to have the water and the hill and the reservoir to do all that. But it can store huge, it's a very efficient way of storing energy, and can be used if the geography is appropriate and lends itself to that. We had previously looked at this idea when we were talking about wind power of pressurized storage of air. So you make a big tank and underground and pressurize it so you can store energy that way. I haven't seen or heard about large scale examples of doing that sort of energy storage. Um, Check the demo for examples of capacitors. Right now, batteries are the primary small scale technology that is being used to store energy. And of course, you can imagine that if everybody has an electric car, or if all cars are electric cars, if they're plugged into the grid at night, can store excess electric energy and deliver that energy. So instead of using the battery to drive your car around at night, it could be plugged into the grid and supplying electricity for your home. And then in the morning, it charges up, or you make sure that you left enough charge in there to take care of your morning drive and let it charge up the rest of the way in the daytime. And this idea of sort of a broad scale distributed use of batteries for storage is also discussed at length in Sustainable Energy Without Hot Air. So that's optional reading. I encourage you to take a look at that as well.